Hi, this is a recording for Stats Unit 1A, the video on the definition of probability. As you can see, I've written to you that probability is a measure of the extent to which an event is likely to occur, and this measure is found by taking the ratio of the favorable cases to the whole number of cases possible. So a place where you often hear probability mentioned is in weather. So if you're watching the weather forecast, it's not that tomorrow we have a 50% chance of rain, for example, because it either will rain or it won't rain. It might be something like there's a 50% chance of rain because on 50% of the days that are similar to the one we're about to experience, that there was rain on half of those days. So it would be a ratio of 50 out of 100, or 1 out of 2, or 10 out of 20, something like that. That would give us that probability. Let's take a look going on. The definition of sample space is important. A sample space of an experiment is the set of all possible outcomes for that experiment. So for example, if you're talking about the event of drawing a card out of a deck of cards, there are 52 different cards in a deck of cards, which means that the sample space has 52 elements to it, and those elements are each of the cards in the deck. If you were rolling a typical pair of dice, each die has 6 sides, which means that when you roll 2 dice, there's 36 different outcomes, or 36 elements in the sample space. That's important because when you find probability, as you saw on the previous slide, you need to take the ratio of the number of outcomes over how many total outcomes there are in order to find a decimal or percent or a fraction that represents your probability. You need to know how many elements are in the sample space in order to be able to do that. There are 2 different kinds of probability that we will make reference to in a global sort of sense. One is experimental probability, and the other is theoretical probability. As you might suppose from looking at the actual word here, experimental probability is where you actually run some sort of an experiment. And so that's the critical part of this. So this would be something like we want to know how many different times we get a 6 when we roll a die. So we roll a dice, roll one of our dice 20 times and we count how many 6s there are. So we actually do something. Okay? We actively act something out and we do some counting. We keep some data. All right? For theoretical probability, it is exactly as that word would suggest. It's something more of a theory. So this is mathematical and in theory. Not an experiment. Oops, I'm sorry. I don't know why that did that. Using a different laptop than I usually do for making videos, and it's a little bit weird. So this is mathematical and no experiment. Okay, let's go on. All right, so the next question is actually a problem. Find the theoretical probabilities for each of the following events. The first event is the event of flipping heads on a coin. Well, we want to think first about our sample space. So since the coin would have 2 different outcomes, either heads or tails, we're going to say that there's 2 elements in our sample space. And then out of those 2, exactly one of them is heads. So we would say that there's a probability of 1/2 or 50% if we wanted to write it as a percent. A 50% probability of flipping heads on a coin. Oh my goodness, this machine is not the best. Okay, keep on going. The next one says the probability of rolling a 6 on a standard die. Well, a die is a cube, and a cube has 6 faces to it, or 6 sides. So the bottom number for our sample space is 6. And then out of the cube that we would roll, this is my rendition of a die, there's one side that looks like this, and that is called rolling a 6. So how many 6s are there on this cube? Oy, I do not know what I'm doing wrong. How many 6s are there on this cube? There's exactly 1. Okay, so 1 out of 6 would be the probability of rolling a 6 on a die. 6 because there's 6 sides, 1 because there's 6. The next one says rolling an even number on the standard die. So here's my, again, excellent picture, just kidding, of my standard die. And out of the different outcomes on this die, there's a 2, there's a 4, and there's a 6 that are all even numbers. So I would say that my probability for this last one is 3 of the outcomes are evens out of the 6 sides. And we can reduce that to be 1/2, or we could write it as a percent if we wanted to, or a decimal even. The next slide shows you that there's a picture here of part of a deck of cards. This is exactly 1/4 of a deck of cards. It shows all of the different cards that are possible in one suit. So a deck of cards has 4 suits. They are called hearts and diamonds. Hearts are in this picture. And hearts and diamonds are both red. And clubs and spades are the other 2 suits, and they are both black. And so this shows 13 cards. They range from an ace, then you count 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's something called a jack, a queen, and a king. The jack, queen, king are called face cards. Ace is sometimes played as the highest card in the suit. Sometimes it's played like a 1, like the lowest card in the suit. It depends on the game that you're playing. Now, the reason I started talking about cards is because cards are often used as a context for a lot of probability questions. And so you do need to have some awareness of what a standard deck of cards is in order to understand those particular problems. All right, our next slide says find the theoretical probabilities of the following if the event is draw a card from a standard deck of cards. So imagine someone has a deck of cards and they fan them out and they're all face down, so you don't know what card you're picking. You want to figure out the probability that you draw, say, a heart. Well, one way to think of this is to say there's 13 hearts. I just told you that on the previous slide. There's 13 hearts in a deck, and the deck has 52 cards. That fraction reduces to 1 out of 4. And this should make sense to us as well because hearts are one of the 4 suits in the deck. And so we would have a 1 in 4 chance of drawing a heart. The next one is the probability of drawing a black card. Well, there are 26 black cards in the deck because I told you 2 of the suits are black. Clubs and spades are black. And so each suit has 13 cards. 13 and 13 make 26. So 26 of the 52 cards are black. You could think of reducing that. It reduces to 1/2, which also should make sense because 1/2 of the deck of cards are made up of black cards. The other half are made up of red cards. The next one is probability of drawing a king. There is a king in every suit. So that means there are 4 kings in the whole deck out of the 52 cards, which means 1 in every 13 cards is a king. And that should make sense because we said that there are 13 cards in a suit, and one of those in each suit is called a king, so 1 out of 13. Find the probability of getting a red 2. Well, there's a 2 of hearts, and there's a 2 of diamonds. So that means there are 2 red hearts out of the deck of 52 cards. If we reduce that fraction, that's 1 out of 26. Now, someone out there is thinking, do we have to reduce the fraction? No, I actually do not care if you reduce the fraction or not. That means the same exact number. It doesn't bother me. Okay, the next one, probability of getting an even numbered card. Okay, we need to think about these words, even numbered. So if we look back at that previous slide, the even numbered cards here, let's get my eraser for a second. I'm catching on to this new laptop. Can you tell? I haven't had an issue for a little bit. Okay, so the even numbered cards are 2, 4, 6, 8, and 10. You might say, well, how about the queen? Should she be counted as an even number? I would say no. The Q is not a number, so that wouldn't be an even number. But you can see here there's 1, 2, 3, 4, 5. 5 even numbered cards in the hearts. So that means that there are 20 even numbered cards in the whole deck of 52. Okay, and if you look back at the slide, you'll see that that certainly must reduce to 1, 2, 3, 4, 5 out of 13 because every suit is going to work the same way. So this would be 5 out of 13 if we did reduce. The last one here says probability of drawing a number that is less than 4. Let's look back at that slide again. If I wanted to draw a number that was less than 4, let's see which ones I would have as options. 2 is a number that's less than 4. 3 is less than 4. Is 4 less than 4? I don't think so. 4 is equal to 4. It's not less than 4. And the ace, again, I would say I wouldn't count that because that's not actually a number. Sometimes aces are played like ones, but not in every game. And so it's not actually numbered as a 1. And this said a number less than 4. So I would say that we have 2 cards in each suit. So we could write it as 2 out of 13 in a given suit, which would be the same as having 2 cards in each suit. So that would be 8 out of 52. Either of those would be fine answers. Okay, moving along. For this next part, I want you to try the following on your own. So I need you to pause the video and then come back and see if you got your answers right. Okay, so please hit pause now on the video and then restart once you have answers. Don't cheat on this or you're cheating yourself of the opportunity to practice. Okay, thanks for actually trying those on your own. Here are our answers. We are looking here at a jar that has 8 marbles total. This is the composition of those 8 marbles. So the probability of green is 2 out of 8, which would reduce to 1 out of 4. Green or red, so either one, we would add together the green and the red. Get 5 out of 8. Red or yellow is going to be 6 out of 8. Probability of blue is 0 out of 8 because there are 0 blues. 0 divided by 8 is 0. The probability of red or green or yellow is 8 out of 8 because there are 8 that are this or this or this. And 8 divided by 8 is 1. So notice that in probability, the largest possible answer is going to be 1, always. And the smallest possible answer is going to be 0, always. If we wrote those as percents, that would be 100% and 0%. Now, notice in the previous question, the probability of green, what was that again? The probability of green was 2 out of 8 or 1/4. The probability of red or yellow, let's look at that. There was 5 red and 5 yellow, or excuse me, 3 red and 3 yellow. Getting a little tired, I guess. So that was 6 out of 8, which was 3 out of 4. So really what we just figured out is the probability of green was 1/4, and the probability of not green, the things that weren't green, was 3 out of 4. 1 out of 4 and 3 out of 4 add up to 1, which we said was the biggest probability answer we could have. When you have probabilities that add up to 1 or add up to 100%, those are referred to as complementary probabilities. They are 2 parts of the whole. We have green and we have not green. Those are opposites. And so their probabilities will be complementary. And together, the 2 events, green and not green, those 2 together make up all the outcomes in the sample space. Sometimes in a problem, it's easier to find the complement and then subtract your answer from 1 rather than find the probability of the event directly. Just bear that in mind. It will come up. It will come up in particular on a worksheet coming up called Worksheet A. It's going to come up several days from now. But just bear that in mind. Sometimes it's easier to find the opposite probability and subtract that answer from 1 to answer your question. I hope that this has been helpful for you, and I'll see you in class. Bring your materials to class. Thanks a lot.